Okay, so our topic for today is the chapter 1 of class 9 physics, which is measurements and experimentations. Okay, now what is this chapter about? So this chapter actually deals with the different units which we use in physics and the different definitions of those different physical quantities like length, mass, time, and the instruments which we use to measure those length, mass, and time. Okay, so this is in brief about this chapter. Today we'll be discussing the first part of this chapter. The first part is systems of unit and units in SI system. Okay, so we'll be discussing about the different systems of unit and the units which we have in the SI system. Now before we proceed to this chapter, you need to know something about science and physics, about the scientific method which we apply, because once you understand the scientific method, you'll understand what is measurement and why we require measurement. Okay, so as you know, science is a systematic attempt to understand natural phenomena in as much detail and depth as possible. So whatever you observe in nature, we study that thing, we reason out that thing, that is science. Okay, so science is actually exploring, experimenting, and predicting from what we see around us. And since physics is a branch of science, it also follows the scientific method and the scientific approach of studying anything which you observe in nature. Okay, so what is the scientific method? The scientific method involves few steps. Okay, like every law or theory which you have studied till now have gone through this scientific method. So the first step is, whatever you see in nature, suppose you want to reason out about it, the first step is observation. Unless you observe any particular phenomena, you're not going to reason out anything. Suppose an apple fell on Newton's head and Newton observed why it fell downwards. So that was an observation which he did, and then curiosity arose and he started researching about it. Similarly, an eclipse happening, that is an observation which you have done. Now you want to reason out why that eclipse is happening. Okay, so the first step is observation. Observation involves whatever you are observing about any particular phenomena taking place. Okay, now next what you do is, you will go in the lab and try to replicate that particular observation in a controlled experiment format. That means you will try to replicate the phenomena which you just observed. Suppose you observed an eclipse happening, so you will try to replicate it in the lab, try to make a model of it in the lab. Like suppose you'll take a light source, a big light source, suppose a big bulb, and label it as sun, and you'll take two balls, small balls, like suppose one you label it as earth and the other you label it as moon, and then will try and do experiments and find out, or you will try to put the earth, suppose over here, or the moon in between the sun and the earth. You'll try to replicate the observation which you observed in nature. You'll try to replicate that thing in the lab. Okay, now once you have that particular phenomena happening, the third step is qualitative reasoning. So once you are able to replicate that phenomena in the lab, you will try to reason out why that particular phenomena happened. Now what will you use to reason out? You will use the logics and the works of earlier physicists based on that particular topic. Okay, so you will try to reason out why that particular thing is happening. So in the case of eclipse, you will figure out that shadow is being cast. Okay, so which is causing the eclipse to happen. The fourth is the one which we will be dealing with, and that is quantitative reasoning. Now quantitative reasoning means we'll be doing number based reasoning. Now number based reasoning involves, like suppose you will try to now find out what will happen if we increase the distance between the sun and the earth, or increase the distance between earth and the moon, or decrease the distance. So you'll be noting down these details, like increasing the distance by this much had this effect, decreasing the distance by this much had this defect, this effect. So this number based reasoning which you're doing actually is called quantitative reasoning. Now since this involves numbers, and that is our topic of discussion, measurements, so we'll be going into this in a little depth later on. Next, after you have done the quantitative reasoning, the fifth point is mathematical modeling. Now since you have quantitative reasoning with you, so you now know which factors influence that observation. That means whether increasing decreases the shadow, increasing the length decreases the shadow, or increases the shadow. So once you have that, you can make a formula. So this is actually making a formula from the quantitative reasoning which you had, mathematical modeling. The next one is, after you have a formula, now what you will do is you will try to predict. You will try to predict based on that formula. So suppose you have a formula for eclipse, and now you can predict, okay, so the next eclipse is going to happen next week at so and so time for 10 minutes. Okay, so you are predicting based on your formula. Now that prediction may be correct or may be incorrect. So what needs to be done? It needs to be verified. Okay, so verification is the next step. So in that next week we'll see if the eclipse happened at the stated time for the stated duration or not. So suppose it happens that from a formula we figured out that the eclipse was supposed to happen for 10 minutes, but now we see it happening for 7 minutes. That means there is some correction needs to be done to a formula. So the last step is correction. Okay, and it may also happen that the formula was correct and no correction is needed. So this is the entire step. Once every time that formula gives us the correct result, like we have now, we can predict when an eclipse is going to happen and at what time is it going to happen and for how much duration it is going to happen. Now we have a perfect formula for that. So once we have a perfect formula, that becomes a theory or a law which we study in physics. Okay, now remember one thing, the basis of all this scientific method is observation. Now this observation depends from person to person. A person may observe something regarding a phenomena while the other person may observe something different regarding that particular phenomena. So observation, if the observation is faulty, the entire process will be faulty, and it has happened in physics earlier. Like take the example of the speed of sound. Newton came up with his observation of speed of sound, and from his observation he gave us a formula for speed of sound. And then when we were verifying his formula, we found that it is not giving us the correct result. That means Newton's observation had some fault. And then later on, a physicist with the name of Laplace, he gave his different observation about the speed of sound, and then he came up with his own formula, and when we verified his formula, it was giving us correct result. So Newton's observation was faulty, so we reject that particular formula which he had said. So this is the scientific method or the scientific approach. Now why are we studying this? So if you see this quantitative reasoning part, okay, this deals with number based reasoning. Now number based reasoning, you have to know which physical quantity will be represented by which unit. Suppose length is a physical quantity, it will be represented by whether meter, kg, second, or what. You need to know that, and that is our topic of discussion, measurement and experimentation. So let us take an example. Suppose we have a rod. Okay, we have a rod and you want to find out what is the length or the area, or what is the dimension of this. Okay, the process of finding the value or the dimension of it is called measurement. Okay, so remember, how will we find out the length of this? What will you do? You will take what? You will take a standard, suppose 1 meter scale. You will take a scale of 1 meter, and then this particular scale, you will try to place it on this. Suppose till here is 1 meter. Next again you will place till here is 1 meter, till here is 1 meter, till here is 1 meter, and till here is 1 meter. So you see that this 1 meter scale which we took as a reference point is lying 5 times in this rod which we took. So since the reference value was 1 meter, we can say the length of this is 5 meters since it is lying 5 times. Okay, so this process which we just did, the process of comparison of the given physical quantity, this particular rod, okay, with the known standard quantity, so this particular ruler, this process is called measurement. Okay, so what is measurement? The process of comparison of the given physical quantity with the known standard quantity of the same nature, that is called a measurement. Okay, now this known standard quantity which we took, this was fixed, this was not changing, this was having a constant magnitude. Now this was used to measure the magnitude of this particular rod. Okay, so this is called a unit. So what is a unit? It is the quantity of a constant magnitude which is used to measure the magnitude of other quantities. So in this case, this was the unit which we used to measure the length of this rod. Okay, now any physical quantity can be represented as having a numerical value which we call the magnitude and a unit. So we'll have a numerical value and a unit. So if we are able to represent any physical quantity in this format, then we have actually done measurement of that physical quantity. Understood? Now you have to understand a few things, like suppose if you are asked to explain the statement, the mass of a given amount of sugar is 5 kilogram. Now if you are asked to explain this statement, what does this statement mean? So first you have to identify in this is the physical quantity which we are talking about. So this is the physical quantity mass. Okay, next this value is the numerical value. It's the numerical value, and this kg is the unit. So what does this statement means? It means that the mass which we are measuring, its unit is kilogram. Remember, the physical quantity which you are measuring, its unit is kilogram. So the physical quantity mass which we are measuring is its unit is kilogram, and that kilogram is contained 5 times in this given amount of sugar. I'm repeating the statement. It means that the mass is measured in the unit kilogram, and this unit is contained 5 times in the given quantity of sugar, as you saw in the example of a ruler over here. Okay, so this was the unit 1 meter, and it was contained 5 times in this length. So similarly over here, this kg is contained 5 times in this given amount of sugar. Okay, our next topic of discussion is the characteristics of a unit, the features which these units should have. Like any unit which we define, which we have, which we use, must have certain characteristics. The first one being, the unit should be of a convenient size. Now remember, had 1 meter been very long, we could not have been able to measure or even raise that particular object of 1 meter to measure anything. Okay, so it should be of convenient size. Had 1 kg been so heavy, we could not have been able to measure anything using kg. Okay, so it should be of convenient size. The second point is it should be well defined. It should be well defined, or we can also say it should not have any ambiguity or confusion in its definition, because if we are able to define it properly, then the unit is of convenient size and it is suitable for us to use. Okay, the third one is it should be reproducible. Now, what do you mean by reproducible? That means, now this unit which we are taking as 1 meter, suppose this has already been defined somewhere, okay, in Paris. Now it should be reproducible in the sense that every time we want to measure anything, we don't have to go to Paris. Okay, this length which is defined as 1 meter, suppose someone goes to Paris, some manufacturer measures how much is this length, and then he comes back and he can make instrument based on this particular length. So it is reproducible. He is able to replicate that particular length. Okay, if this particular object would have been of inconvenient size or would not have been would have had ambiguity in its definition, then it would not have been reproducible also. So they are all related. The fourth point is it should not change with space and time. So it should not happen that once you go to Paris, the value of 1 meter is something else, and then when you come back to India, since the place changes, the value 1 meter changes. No, it should not happen like that. Similarly, in the morning, 1 meter is some this much length, and then in the evening it becomes this much. So this such type of unit, such type of thing cannot be taken as a unit. Okay, so unit should have the following 4 characteristics. Now remember, out of these 4 characteristics, the first, the last 3 are the ones which make a unit to be accepted as international unit. Okay. Now next topic of discussion is the types of units. Now units, as you know, represent physical quantities. So in physics, remember, physical quantities are divided into 2 types, 2 categories, and the categories are fundamental physical quantities and derived quantities. So similarly, the units are divided into fundamental units and derived units. Okay, now what are fundamental units? So it is a unit which is independent of any other unit, and it cannot be expressed in terms of other physical quantities. Now what does it mean? It means that the fundamental units are the basic building blocks, okay, are the basic units using which you can make other units, but these are independent. These fundamental units are independent of any other units. That means they cannot be made using any unit. Okay, they cannot be expressed in terms of other physical quantities, but they can be used to express other physical quantities. Okay, now as you know, the fundamental physical quantities have fundamental units. Okay, so you are aware of few fundamental physical quantities like that of length. Its fundamental unit is meter. Then you have mass, it has kilogram. Then you have time, it is second. Then you have temperature, Kelvin. Then you have luminous intensity, denoted by its unit is candela. Then you have the electric current, unit is ampere. Then you have amount of substance, denoted its unit is mole. Then you have angle, having radian as its unit. And then you have solid angle, having steradian as its units. So you have to remember these physical quantities and their fundamental units. Okay, now remember, if you are asked a question, name any two fundamental units, then you will write any two from this side. But if you are asked to name any two fundamental physical quantities, then you will write any two from this side. Okay, do not confuse between physical quantities and units. This is a very common mistake which the students do. Okay, so you have the 9 fundamental quantities with their fundamental units listed over here. Now come to derived units. Now derived units are the units of the quantities which can be expressed in terms of fundamental units. So remember, derived units are made up of using fundamental units. So the physical quantities they represent are made up of fundamental units. Okay, now example you can take as, suppose, area. You know the unit is meter square, so meter square is a derived unit. How? Because it is made up of meter into meter, and these are fundamental units. Similarly, if you have density, the unit is kg per meter cube. So remember, this is the derived unit. It is made up of kg and meter into meter into meter. All these are fundamental units. Okay, so these are derived units. Okay, our next topic of discussion is the different system of units. System of units. Now remember, the three fundamental, out of the 9 fundamental quantities, the top three, the length, mass and time, okay, these three have been assigned different units based on the places they have been used. Okay, so we will be discussing about the system of units which have these length, mass and time with different units. Okay, so the first system is called the CGS system. CGS system. Now this is, the full form is centimeter gram second system. Now this is also known as the French system, so you can say that this system was used by the French. Now in this, length was denoted by centimeter, mass was denoted by gram, and time was denoted in second. Okay, the second system is the FPS system. Now FPS stands for foot pound second system. This was used by the British, so this is also known as the British system. Now since we have been ruled by the British for so long, that this particular system has its roots within us. Okay, so unknowingly also we are using it still. So in this, length was having the unit foot, mass was having the unit pound, and time was having the unit second. Now you have been using this particular, especially mass, when you go to buy bread or a cake in a shop. You often ask the person to give the bread in terms of pound, half pound or 1 pound you ask. Okay, so we are still using this unknowingly. Similarly, area of any place, suppose we measure in terms of square foot. Okay, so these are all being used still by us, but then this is not what should be used, as these are all old systems replaced by the new system. Okay, the third one is the MKS system. MKS system. Now MK stands for meter, kg, and second system. Is also known as the metric system. Okay, in this, length was denoted by meter, mass by kilogram, and time in seconds. Now remember, all these three system of units are old and have been replaced by a new standard system which we are going to study now. So the new standard system is called the SI system, or better known as the Standard International System. Now this is also known as System International de Units. The full form of SI is actually System International de Units, but then this is also abbreviated or expanded in the form of Standard International System. Now in this system, what was different was, in the earlier three systems which we studied, only length, mass, and time were given units, assigned units. But in this SI system, all the 9 fundamental quantities have been assigned units. Okay, so I'll just show you those fundamental quantities with their SI unit and their symbols. Okay, so here you have all the 9 fundamental quantities listed with their SI unit and their symbols which we use. So just remember these values. Okay, now next we come to the in-depth study about the 3 fundamental quantities: length, mass, and time. Actually, in-depth study about the units. Okay, the different units which these fundamental physical quantities have. So first is units of length. So we'll be studying about the different units of length. So the first thing is, the SI unit is meter, so we are aware of this. Now we are asked to define meter. Okay, now I'm writing the definition of meter here, then I'll explain you how it comes. So 1 meter is defined as the length of the path traveled by light in vacuum or air, you can write, in a time interval of 1 by 299,792,458 second. Now this is the definition of a meter. This is the actual definition. If you are asked to define meter, this is what you are going to write. Now how does this definition comes? So as you are aware that the speed of light in vacuum, speed of light in vacuum is taken to be 3 into 10 to the power 8 meter per second, which is actually 3 and then 8 zeros meter per second. But this is not the actual value, this is the rounded value. Okay, the actual value is 299,792,458 meter per second. Now this actual value is rounded off to this. Okay, so what does this mean, that the speed of light in vacuum is 299,792,458 meter per second? It means that light travels a distance of 299,792,458 meters in 1 second. So if we use unitary method, we can say light travels a distance of 1 meter in 1 upon 299,792,458 second. So you can see the definition now. 1 meter is defined as the length of the path traveled, that means the distance traveled by light in vacuum in a time interval of 1 by 299,792,458 of the second. So this is the definition of meter. But know that the meter was defined earlier using something else. Okay, what happened was a rod was taken, okay, platinum iridium rod. This rod made up of platinum and iridium, and there were 2 marks made on this rod. Okay, and the distance between them was taken to be 1 meter. This was the standard used. Okay, and this is kept still in Paris. Okay, so this was the old definition of meter, but now you will use the new one which I have informed earlier. Okay, now we come to few smaller units of meter or length, you can say. The first one is centimeter. It is denoted by cm, and 1 cm is equal to 10 to the power minus 2 meters or 1 by 100 meters. The second unit is millimeter, denoted by mm. So 1 millimeter is equal to 10 to the power minus 3 meters, and that is actually 1 by 1000 of a meter. The third one is micrometer, also known as micron. The unit is micrometer. This is, and 1 micrometer is 10 to the power minus 6 meters, or you can say 1 by and then 6 zeros over here, meters. Okay, the next one is nanometer, denoted by nm, and 1 nanometer equal to 10 to the power minus 9 meters, and you know how to write this with 9 zeros. Okay, so in order to convert centimeter to meter, you will have to divide that particular value with 100. Okay, and if you want to do opposite conversion, now if you want to convert centimeter to meter, you'll have to divide by 100. You have to use this formula, okay? But if you do opposite conversion, that means meter to centimeter, and you'll have to do opposite of it. Instead of dividing, you'll have to multiply it with 100. Okay, same goes for all these. Now we have some bigger units also. The bigger units. Now of them, the most common one I'm writing, so this kilometer. Kilometer denoted by km. Okay, so 1 km equal to 10 to the power 3 meters, or you know is 1000 meters. Okay, there are other prefixes also, like kilo is used before meter. Kilo is used before meter, so it means 10 to the power 3. Okay, similarly nano is used before meter, means 10 to the power minus 9. So these are prefixes, like micro is a prefix, milli is a prefix, centi is a prefix, kilo is a prefix. So assigning these prefixes to any SI unit, like kilometer, like meter, we add kilo, then what will happen? It will be a multiple of 10 to the power 3. Similarly, if we add nano before meter, it will be a multiple of 10 to the power minus 9. So I'm showing you a table containing those values. Just go through them once. Okay, so these are some prefixes which are used for big measurements, and these are some prefixes used for small measurements. Okay, so like suppose the basic unit is suppose meter, the SI unit is meter, and you have suppose out of this giga written before it, giga. Now what does this mean? It means since it is a big measurement, so it means 10 to the power 9 meters. Gigameter is 10 to the power 9 meters there. Similarly, if you are suppose given 5 gigameter, so it will be 5 into 10 to the power 9 meters. Okay, similarly for small measurements, like suppose you have picometer. Okay, picometer, from the table you can see pico is 10 to the minus 12, so this is actually 10 to the minus 12 meters. So if you are given suppose 75 picometer, so if you want to convert it into meters, it will be 75 into 10 to the power minus 12 meters. Okay, so you will have to remember the values given in these tables. Now we come to some non-metric units of length. Non-metric units of length. Now what are these non-metric units of length? These are actually not having any of those above prefixes, okay, which I have given in the table. So these non-metric units of length have bigger units and smaller units also. So the smaller units from the non-metric units, the smaller units, you have angstrom, denoted by this, and 1 angstrom equal to 10 to the power minus 10 meters. Okay, similarly you have Fermi, denoted by small f, and 1 Fermi equal to 10 to the power minus 15 meters. Okay, then you have the bigger units also. The bigger units, of the bigger units you have astronomical unit. So 1 astronomical unit, denoted by AU, equal to 1.496 into 10 to the power 11 meters. Okay, next is light year. So 1 light year is denoted by LY, is equal to 9.46 into 10 to the power 15 meters, and 1 parsec is equal to 3.08 into 10 to the power 16 meters. Now remember, these are bigger units, especially light year and parsec and astronomical units. These are used for measuring the distances between heavenly bodies, or universe related distance measuring. Okay, so if you are asked to find suppose the relation between light year and parsec, so what you will do is you will divide parsec by light year. and you will get the value. So I'm just writing it over here. So 1 parsec is equal to 3.26 light year. You can get this relation. Okay, similarly you can find how much is 1 parsec in terms of astronomical unit. You divide the value of this 1 parsec by this value. Okay, now here you need to note one point, that this light year, even though it has year in its name, is not a unit of time, it is a unit of length. This is a very common mistake. Light year is given and then you are asked which physical quantity it represents. The students normally write time since it has year in it. Okay, but remember, it is wrong. The correct physical quantity which light year represents is length. Okay, now this was all about the different units of length. Now we move on to the units of mass. So the units of mass. Now you are aware that the SI unit is kilogram or kg. And how do we define 1 kg? Again I'm writing the definition. So 1 kg is the mass of 1 liter of water at 4 degree Celsius. 1 liter of water at 4 degree Celsius. Okay, now what was the older definition of mass? So if you remember the platinum iridium rod, yes, this particular rod, in which we had marked 2 points to find the distance between them as length. So the weight of this platinum iridium rod, the mass of this, was taken to be 1 kg. Okay, so a random rod whose mass was considered to be 1 kg. But now if you are asked to define mass, we will define it as this. Understood? So now we will have to study about the subunits of kilogram. So you have the smaller units, you can say the smaller units of kilogram. Now what is the first one? The first one is gram, which is denoted by G, and you know 1 gram is 10 to the power minus 3 kg. Similarly the second one is milligram. Milligram is denoted by mg, and 1 mg equal to 10 to the power minus 6 kg. Okay, now we have the bigger unit or the multiple units. First one is quintal. Okay, and quintal is 1 quintal is 100 kgs. Similarly you have metric ton, and 1 metric ton equal to 1000 kg. Now if you see these two, you can say 1 metric ton is equal to 10 quintal also. Okay, now we come to the non-metric unit of mass. Remember, you'll have to remember all these units, all these subunits, all these bigger units, smaller units. So the non-metric unit of mass. Then the non-metric unit of mass, you have the first one as atomic mass unit. Atomic mass unit. It is also known as the unified atomic mass unit. Now it is denoted by AMU, and 1 AMU equal to 1.66 into 10 to the power minus 27 kg. Similarly the second one is solar mass, and 1 solar mass is equal to 2 into 10 to the power 30 kg. Okay, now atomic mass unit is usually used to measure the mass of fundamental particles like electrons, protons and neutrons, and solar mass is simply the mass of the sun. Okay, so this was all about the unit of mass. Now we move on to the units of time. Units of time. Now you are aware of the SI unit. SI unit of time is second, denoted by small s. Okay, and how do we define 1 second? So again, see the definition. 1 second is defined as 1 upon 86400th part of a mean solar day. Now what is this actually? So again we come back to the concept of unitary method. One solar day. Solar day is actually one day has how much hours? 24 hours. 24 hours is 24 into 60 minutes, and that is 24 into 60 into 60 seconds. So you can say if you multiply you'll get 86400 second. You can say one solar day has 86400 seconds. So in the unitary method we can say 86400 seconds make up one solar day. Okay, so 1 second makes up 1 upon 86400th part of a solar day. This is normal unitary method. Okay, so now if you see the definition, 1 second is defined as 1 by 86400th part of a mean solar day. So I hope the definition is clear now. This is one of the definition, or the common one, which is used. If you are asked to define second, you can go with this definition. There's another definition, and that definition is second definition of second. 1 second is the duration in which cesium atom vibrates 91926317770 times. Okay, so this is another definition of a second. Now coming to the smaller units of time. So smaller units of time, the first one is 1 millisecond. Millisecond is denoted by ms, and that is equal to 10 to the minus 3, because milli is 10 to the minus 3. Okay, the second one is 1 microsecond. Microsecond is mu s, so that is equal to 10 to the minus 6 second, because micro is 10 to the minus 6. Third one is 1 nanosecond, and that is denoted by ns, and that is 10 to the minus 9, because nano is 10 to the minus 9. And the fourth one is 1 shake, and that is 10 to the minus 8 seconds. Okay, 10 to the minus 8 seconds. So these are the smaller units of time. Coming to the bigger units of time. Then the bigger units of time, you have 1 minute, and that is equal to 60 seconds. Next is 1 hour, and that is equal to 60 minutes. So 60 into 60 is 3600 seconds. Then you have 1 day, and we have seen one solar day has 86400 seconds. Then you have 1 year, and that has 365 days if you're talking about normal year. So 365 days, you multiply it with 86400 second, because every day has that much second. So whatever value you get over here will be the 1 year with respect to seconds. Okay, Next is one leap year. Now what is a leap year? You are aware of what leap year is. If in terms of days, it has 366 days. So 366 days into again 86400 second. Whatever value comes, that much is the value. Okay. Leap year, you can Google up for more details, like what is a leap year actually. So February has 29 days in it, but then from the year, how will you figure out if it is a leap year or not? So I'm just stating the rules. If it is a non-century year, okay, non-century year means like 2004, 2016, 2020, these are non-century years. So if it is non-century year and divisible by 4, then it is a leap year. Okay. But if it is a century year like 2000, 2100, 1600, then in order for it to be a leap year, it should be divisible by 400. So this is the general rule. You can Google up for more details. Okay, the sixth one is one decade. One decade is 10 years, and then 10 years, 10 into 1 year is how much? If you multiply this, you will get 3.16 into 10 to the power 7 seconds. So this comes out to be 3.16 into 10 to the power 8 seconds. Okay. Similarly, 7 is 1 century, and 1 century is 100 years, and then you can get similarly 100 into 3.16 into 10 to the power 7 seconds. So this will give you 3.16 into 10 to the power 9 seconds. And next we have 1 millennium, and that is 1000 years, and that is 1000 into 3.16 into 10 to the power 7 seconds. So that comes out to be 3.16 into 10 to the power 10 seconds. Okay, now these were the units of time. Okay, now here we have some examples of derived units. Okay, so we saw some examples of derived units like area and density. So you have a few of them listed over here. So just go through them once. Like area, its formula is length into breadth, and its derived unit is meter into meter, because length is also having a unit meter, breadth is also having a unit meter, so its unit meter square is a derived unit. Okay, similarly for others also, you can see force also, its formula is mass into acceleration, and how it is made up of the fundamental units. So go through them once. These are examples of derived units. Now we come to the last part, last topic which we are going to discuss, and that is the general guidelines for writing the units. So you have to follow some rules and regulations while writing any of the units. What are those? I'll be listing them down. So the first rule is that if a symbol for a unit is not named after a scientist, okay, if it is not named after a scientist, if unit is not named after a scientist, then it is written in small letter. Okay, like suppose meter is an example. It is not named after a scientist, so you write it like this. Okay, you write it in small letters like this, small m. Okay, similarly second is not named after a scientist, so you write it with small s. Okay, this is the first guideline. The second guideline says if unit is named after a scientist, named after a scientist, okay, then the first letter of the unit of his name, you can say of his name, is written in capital. That means take the example of Newton. Okay, if Newton is a unit, you will write it as capital N because it begins with N, so you'll write that N as capital N. Similarly, Joule is an example, so it is named after a scientist, so you'll write it as capital J like this. Okay, Pascal is another example, so if you have Pascal as the unit, you will be writing it as capital P small a. This is the unit. Okay, the next guideline is that if you're writing the unit in full, okay, if writing the unit in full, then uh, it is always written in small letters. Now what does this mean? Now it does not depend whether the unit is named after a scientist or not. If you're writing it completely, like suppose if you want to write meter, you will write meter like this, complete. You'll not write capital M, not write like this. Okay, similarly, Newton, if you want to write complete Newton, then you will not write like this, Newton. Okay, if you want to write suppose 10 meter, you will write it like this and not this. You want to write suppose 5 Newton, you will write it like this and not this. Okay, the fourth guideline says, okay, if a unit is made up of multiple units, like if compound unit is there, okay, if compound unit means made up of more than one unit. If compound unit, then write the units with a dot or cross or space in between. Now what does it mean? It means suppose the unit is meter per second, so you will write either like this, meter per second, or you will write it as meter per second, or you will write it as meter per second with a space over here. You will not write it as ms minus 1 like this attached. Okay, the next point is, the fifth point is that if you are using compound unit which has a division in it, that means suppose you want to write about kg per meter cube or meter per second. Now we are used to these, but we will not be writing it like this. Okay, we'll not be writing like this. Okay, so compound units which have division must be represented with negative power. Compound unit, I'm writing it over here, compound unit which has division, that means which is formed using division, must be represented in negative power. That means you have to write this as kg per meter cube like this, minus 3 you are supposed to use. Okay, over here you will write m s minus 1. Okay, you will not write it like this. The next guideline is that if a unit in its short form, you are writing a unit in its short form, then you will never write it in plural. Okay, you will never write it in plural. For example, I'm writing it first, a unit in its short form is never written in plural. Now what does it mean? For example, 5 meters you're supposed to write. Okay, so meters, you will not write 5, you will not write it as 5 meters ms. No, ms has a different meaning, it means millisecond. So you are totally changing the physical quantity. This was supposed to be the unit of length, you have made it a unit of time. Okay, so what will you write? 5 meters, you will always write it like this, 5 meter. You will not use a plural, okay, when writing in short form. So these were the guidelines for writing the units. With this we come to the end of our class today. So I hope you have understood the topic properly. If not, go through the recording once again if possible, and try to understand, try to pause and note down whatever I have discussed, whatever I am writing. Try to note it down in your copy. Okay, thank you.